Welcome to Module 4, Part 8. In this section, we are going to discuss the energy band diagram of the MOS capacitor. Consider the case when a negative voltage is applied to the gate terminal. So, when a negative voltage is applied to the gate terminal, the electric field is directed towards the gate terminal. The valence band bends towards the Fermi level. Here, the Fermi level is constant in the semiconductor material since the MOS system is in thermal equilibrium and there is no current into this oxide layer. So, here the charge accumulation takes place. So, under this oxide layer, positive charges accumulate since the gate terminal is connected to the negative side of the battery. The positive charges are attracted towards the gate terminal, as a result of which the gate terminal and accumulate under the oxide layer. Now consider the case when a positive voltage is applied to the gate terminal. When a positive voltage is applied to the gate terminal, the electric field is directed towards the substrate material. So this will attract the negative charges. The holes or the positive charges are moved away from this particular area, as a result of which negative charges accumulate under this particular region. The conduction band and the intrinsic Fermi level bend closer to the Fermi level than that of the valence band. So the space induced in this particular area is called the induced space charge region. Over here in this p-type semiconductor material, majority charge carriers are holes. Since the positive voltage is applied to the gate terminal, negative charges are attracted towards the oxide layer, and in this particular region the charge inversion takes place. Earlier the layer was p-type, now the majority charge carriers are electrons, as a result of which the p-type material is converted to a n-type material. The inversion layer of electrons takes place near the oxide semiconductor interface. Now next, consider the case when a larger positive voltage is applied to the gate terminal. So when a larger positive voltage is applied to the gate terminal, the conduction band bends more towards the Fermi level than that of the valence band. The intrinsic Fermi level is very close to the Fermi level. Larger negative charges or the electrons accumulate under this oxide layer, as a result of which p-type material converts to a n-type material in this particular region, and the induced space charge also increases. Next, we'll consider the case where the substrate material is n-type. In earlier cases, we considered the substrate material to be p-type. Now we'll consider the substrate material to be n-type. Consider positive voltage is applied to the metal plate and the negative voltage is applied to the substrate material. So this positive voltage will attract the opposite charge, that is the negative charges. So these electrons start accumulating just below the junction of the oxide, in the junction of the oxide and the substrate. So there are negative charges over here in this particular junction. So accumulation of electrons takes place in this particular region. Next, if a negative voltage is applied to the metal plate and a positive voltage is applied to the substrate material, negative charges accumulate on the top of this metal plate, and this negative supply will attract the opposite charge, that is the holes. Holes are attracted towards the junction. So this region is the induced positive space charge region where the holes are attracted. So this forms the depletion region now. The electric field is directed towards the metal plate. Next, we'll consider the energy band diagram for this particular cases where the substrate material is n-type and we have applied the positive voltage as well as the negative voltage to the metal plates. So here consider positive voltage is applied to the gate terminal. So when a positive voltage is applied to the gate terminal, the conduction band bends towards the Fermi level, and accumulation of the electrons takes place in this particular region. So the charge inversion, this positive voltage will attract lot of negative charges under the oxide region. Next we'll consider the case when a negative voltage is applied to the gate terminal. So when a negative voltage is applied to the gate terminal, the conduction band and the valence band as well as the intrinsic Fermi level bend. So the valence band and the intrinsic Fermi level are more closer to the Fermi level than that of the conduction band. Here positive charges accumulate under the oxide region. Since the gate terminal is connected to the negative side of the battery, this will attract the positive charges under the oxide region, and here the majority charge carriers will be holes, as a result of which the layer inversion takes place. Initially the layer was p-type. Now in this particular region initially the layer was n-type. Now in this particular region the layer will be p-type. So layer inversion takes place, and when a larger gate voltage is applied to the gate terminal, then the induced space increases. The induced space charge region increases and lot of holes get accumulated in this particular region. So over here, now this is a p-type region. The charge inversion has taken place. So this is about the energy band diagram of MOS capacitor when the substrate is p-type and when the substrate is n-type, and when positive voltage is applied to the gate terminal and when negative voltage is applied to the gate terminal. Thank you.